Imagine you own a watch that lets you travel through time. One day, you get the bright idea to travel back to the 1920s to mess with your grandparents. You press a few buttons, and suddenly you're standing beside old Pappy, who's taking in the scenery at the precipice of the Grand Canyon. Since you've never been the biggest fan of your grandfather, you decide to push him over the edge. Gravity does its thing, and a few seconds later, no more Pappy. But wait, if you killed your grandfather before he ever met your grandmother, you wouldn't have been born to be able to go back in time and kill him. Here's the problem. If you didn't exist to kill your grandfather, you couldn't have killed him. Because you didn't kill him, he's still alive. But that would mean that you yourself would be alive, and now you can go back in time to kill him, and so the endless loop goes on. This is called the grandfather paradox, and it's part of what makes time travel so interesting. The grandfather paradox deals with time travel on a significant scale, but why don't we start with something a little smaller? Let's say you and I are wearing identical watches, and we synchronize them right before I blast off into space. In the space shuttle, I'm traveling at roughly 28,000 kilometers per hour relative to the Earth. If I make a few orbits around the Earth before I return, when we compare watches we'll see that less time has passed for me. A very, very tiny amount of time, but it's there nonetheless. This is called time dilation, and it simply means that according to Einstein's theory of relativity, time measured along different trajectories is affected by differences in either gravity or velocity, each of which affects time in different ways. One example of time dilation is when we compare the passage of time on the ISS versus on Earth. After spending 6 months on the space station, astronauts have aged approximately 0.005 seconds less than those of us here on Earth. Of course, this is a very insignificant amount of time, but it would be much more apparent if the astronauts were able to travel closer to the speed of light. Interestingly, the effects of time dilation are fairly minor, even up to around 70% the speed of light. However, once we reach 75% or so, the effects become dramatic. Now, bear with me here, because this is where things get a bit weird. Possibly the strangest aspect of special relativity is that distances shrink in the direction of motion. When we think of traveling to a point 10 light years away at 90% of light speed, you would expect it to take 11 years, right? That's not exactly the case. To a stationary observer, it would indeed seem to take your vessel 11 years. But to the people inside the vessel, not only time, but distance would dilate, and you would reach that point in only 4.4 years. Want to play with time dilation yourself? I've added a link down below to a time dilation calculator. Okay, that's all really fascinating, but is it really time travel? Perhaps not in the sense that we usually think of it, but according to the nature of space-time, it is. If you were to return home from your 90% light speed trip, you would be almost 9 years older, but everyone back on Earth would have aged 22 years. So in essence, you've traveled 13 years into the future relative to your time in space. Let's look at another example. In the film Interstellar, Cooper and his team land on a large watery planet, on which gravity is 30% stronger than on Earth. This planet is situated very close to a supermassive black hole called Gargantua, which it orbits at 55% the speed of light. Gargantua's mass is equal to that of 100 million suns, and spins at 99.8% the speed of light. The combination of all these factors have the effect of slowing down time relative to the astronaut left aboard the ship by a staggering 61,000 times. That means that 1 hour on the planet is equal to 7 years aboard the ship. When the team makes it back to the vessel after a little over 3 of their hours, their friend had aged by 23 years. The craziest part is that this isn't just science fiction. Those calculations all check out. That's exactly how it would happen in real life. So, in essence, the crew had traveled 23 years into the future. Now, so far we've only explored traveling into the future. Is it possible to travel backwards in time? According to some theories, specific types of motion in space might allow time travel into the past and future if these geometries and motions were possible. However, that's a big if. It would require something called a closed time-like curve, or CTC for short. A CTC is a closed loop in spacetime, which could theoretically allow an object to return to its own past. The science behind time travel to the past is incredibly complex and speculative, and many scientists suspect that it's not possible at all because of the issue of causality. That brings us back to the grandfather paradox. If in fact these scientists are correct in assuming traveling to the past would cause a paradox, then we have our answer. Time travel to the past is impossible. If, however, the Novikov self-consistency principle is correct, then there's still a chance. The Novikov principle states that if an event exists that would cause a paradox or any change to the past whatsoever, then the probability of that event is 0. It would thus be impossible to create time paradoxes. Unfortunately for any would-be time travelers, the Novikov principle is not widely accepted. Another possibility would be the existence of wormholes, which are technically permitted by general relativity. In order to travel through time using a wormhole, it would have to be what is known as a transversible wormhole. Brace yourself for more strange space-time shenanigans here. In order to be able to travel through time using a transversible wormhole, its creation would have to be in one of two ways. Option 1. One end of the wormhole would have to be accelerated to a significant portion of the speed of light, then brought back to the origin point. Time dilation would result in the accelerated wormhole entrance aging less than the stationary one as seen by an external observer. Option 2 requires one end of the wormhole to be placed within the gravitational field of an object with higher gravity than the other entrance, and then returned to a position near the other entrance. This is a difficult concept to grasp, so think of it this way. Imagine you and I synchronized our watches to both display the year 2000. I hop in my ship and accelerate one entrance to the wormhole to near light speed, then bring it back. My watch now reads 2004, and yours reads 2012. If someone were then to enter the accelerated entrance, they would now exit the stationary entrance in the year 2004. The same location, but 8 years in their past. It's incredibly complicated stuff, but an easier way to look at it is by picturing a piece of paper. This paper represents space-time. A wormhole is an area of warped space-time with an entrance and an exit, which you can imagine as the paper being folded back on itself with a hole poked through it. Essentially, you're simply skipping all the time and distance between the 2 points. The problem with transversible wormholes is that you can't possibly travel back further than the initial creation of the wormhole. So really, it's more of a path through time rather than a device that propels itself back and forth through the years at will. It could be useful for people in the distant future wanting to come observe our time, but if we created such a portal today, we couldn't use it to go visit the dinosaurs. One final method that could potentially allow an individual to more or less travel through time is cryopreservation. The branch of science concerned specifically with preserving humans is called cryonics, and the practice has been around since the late 1960s. Cryonics is on the speculative edge of medicine, as its proponents suggest that death is not a singular event, but a process. It would have to be for the practice to be successful, because it's currently illegal for a human to be frozen before they die. When a person has opted to be cryopreserved, their body is prepared minutes after official death. The theory is that by reducing the patient's body temperature to around -130 degrees Celsius, enough brain information will be retained in an accessible state for doctors and scientists of the far future to revive the patient. Temperatures that low inevitably cause significant damage to the human body, regardless of cryopreservation safeguards, so the doctors of today are relying on the development of future technology that will allow the brain to be repaired at the molecular level and restored to functioning condition. If someday technology has advanced far enough to revive cryopreserved humans, they will have essentially time traveled to the future. It's not quite as easy as shows like Futurama make it seem, but it is theoretically possible. And that's time travel in a nutshell. You really can move forward through time by traveling at immense speeds or through cryopreservation, but travel to the past is likely impossible. Of course, the science of quantum physics and time travel is incredibly vast and well beyond the grasp of most normal people, so we may be missing just one crucial element to understanding exactly how space-time works. But who knows? Maybe someone from the far future will show up in our time and give us the key to unlocking the mystery. Or would that cause a paradox? As always, I've included sources and links for further reading in the description. If you enjoyed this video, please take a moment to subscribe to my channel. Your support helps me keep releasing 2 videos every week. Feel free to leave a like or a dislike as you please, and share your thoughts on time travel in the comments. Thanks for watching, and I'll see you in the next video.